So in this video, we're going to do trigonometric limits. I'm going to give you a brief background on what you need to know to be able to solve these trigonometric limits. Then I'm going to give you a guideline for the general strategy of how to solve them. And then we're going to go through some examples to test your understanding and just to solidify what you've learned. So let's begin on what you need to know. Now, it's extremely important for you to learn these two special trigonometric integrals. Here's the first one. The limit as x approaches 0 of sine x over x, that's equal to 1. And then we have the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. So pretty self-explanatory. I don't really need to explain these much in detail. You just need to be able to identify when you can use them and then what the result is. Just a note that I want to make to assist you of identifying it. So how do you know when to use, for example, the first special trig limit? Because we can obviously, or we might see that we aren't always going to get sine of x over x. We may get a form like that, for example, sine of some function over some function, and we need to manipulate that function to get it into this form. So how do we identify, or what's the strategy that we should use? What you want is to identify what is inside the brackets of the sine function or the argument of the sine function. Let's assume that we have, let's say, 3x, okay, as our argument for the sine function or our angle. So we have sine of 3x. What we want to then have or try and manipulate to a point is we want to get to a point where we get 3x in the denominator as well, or maybe it's in the denominator as well. We just want to ensure that what we have in the denominator matches what we have in the argument of the sine function. And we also need to have the limit as 3x. So this must also match with the denominator and the argument of the sine function. Okay, so the limit function or variable must also match with those two there. And this must approach 0. If this is the case, so this matches with that and it matches with that, then this entire thing is equal to 1, regardless of what's in the denominator, what's here or what's here, whatever variable or function it is. If 1, 2, 3 match, then we're going to get 1. Okay, so just take note of that. I'll show you how to handle that in an example that we'll cover. And the exact same thing applies for the cosine special trig limit. Your key is to look at what is inside the argument of the cosine function, and that must match with the denominator and match with the limit. Okay, so that's the first thing that you need to know. Next, let's go on to L'Hopital's rule, or as I'm going to call it in this video, Bernoulli's rule. It's just easier for me to say. And besides, I think for the past 3 years, I've been saying Le Hospital's rule. Okay, so don't say that. It's actually Bernoulli's rule. Okay, if you want, you can say that. I'm going to say Bernoulli's rule. So what does this rule state? How does it work? So let's say I give you a limit to work out, and it's in the form of a fraction, because you have f of x over g of x. I'm going to call it a fraction. So the limit as x approaches c of f of x over g of x, that is equal to the same limit as x approaches c. But notice how we have the derivative f prime of x in the numerator and the derivative g prime of x in the denominator. So all we've done is we've transformed that and said that it's equal to that. We're just going to differentiate the numerator, differentiate the denominator, and then solve the new limit. Okay, those answers are going to be equal. That's all you have to do. But there's a huge condition, and you can only do this under this condition. Here's the condition. If direct substitution for this, okay, the original limit that you have, yields an indeterminate form, such as 0 over 0, or an infinity over an infinity, can be plus minus infinity. Okay, what does that mean? So let's say I give you something, I give you limit x, or let's write it down here. Let's say I give you limit x approaches c of f of x over g of x, right? And what you're going to do is, firstly, you're going to use direct substitution. Direct substitution, as the phrase implies, is directly substitute c into this function. So you're going to calculate f of c, not calculate, substitute f of c in, or substitute c into f of x. and then you're going to calculate g of c. Okay, so you're going to get f of c over g of c. You're going to calculate both those. If f of c is 0 and g of c is 0, that's an indeterminate form. Or you could get an instance where you have an infinity for f of c and an infinity for g of c. You could also have plus minuses on these, doesn't really matter. You have infinity symbols, okay, in the numerator and the denominator. That's when you have an indeterminate form. If that is the case, once you have used direct substitution, what you're going to do is you're going to use Bernoulli's rule, and that basically says, okay, you've got an indeterminate form. All right, no problem. What we're going to do is differentiate f prime of x. So you're going to differentiate the numerator, and then you're going to differentiate the denominator. So you're going to get g prime of x. And then you're just going to take the limit as x approaches c of this. And if it gives you a valid answer, great. That's your answer to the entire question. Okay, if you still get an indeterminate form, then you keep using Bernoulli's rule. So then you would get f prime prime x and g prime prime x. And then hopefully, when you do direct substitution again, you get a valid answer. Okay, so that's all Bernoulli's rule is stating. If you have an indeterminate form, differentiate the numerator, differentiate the denominator, okay, and then try direct substitution there. So let's see this in action in an example. Okay, just before we go to an example, I'll give you some guidelines. So here are the guidelines. The first step is to identify an indeterminate form is present. So if you have an indeterminate form, if that's present, then you're going to use Bernoulli's rule if it's applicable. Right? Obviously, if there's an indeterminate form. And if that doesn't work, then you're going to try and manipulate the trigonometric expression until you can make a direct substitution. So what I mean by that is using your trig formula. Okay, so your reduction formula, possibly double angles, your sine is equal to whatever the case may be, or tangent is equal to sine over cosine. Okay, that's what I mean by manipulate. Okay, so sine over cosine, that's tangent. Okay, or you're going to manipulate your expression to the point where you can use one of the two special trigonometric limits. Okay, so this is a general guideline that you can use. Okay, but obviously what you want to check first is for Bernoulli's rule and then try that. If that doesn't work, then come to step 2 and try whatever manipulation you can think of. Okay, so let's finally see an example. Okay, so take a look at example 1. Pause the video if you want to try it, and then I'll go through the solution. All right, so what I'm going to do in this example is I'm going to follow the guideline that I gave you. Okay, what we're going to do is try direct substitution. So we see that x is approaching 0. Okay, so let's try direct substitution. So if I substitute x in place, 0 in place of sine 5x, I'm going to get sine of 5 times 0, and that's obviously going to be 0. Sine of 0, we know, is 0. So I'm going to get 0 in the numerator. And hopefully you can see that if you substitute 0 in place of the x in the denominator, you're going to get 3 times 0, that's 0. Excellent. I have an indeterminate form. So I'm going to use Bernoulli's rule. Right, so let's use Bernoulli's rule. So we have the limit as x approaching 0 of sine 5x over 3x. That is equal to the limit as x approaches 0. Let's just shrink this so we can do the differentiation. Okay, so now we are going to use Bernoulli's rule. Since this gave us an indeterminate form, we had 0, 0, we can now use Bernoulli's rule. Bernoulli's rule states that differentiate the numerator. So if I had to differentiate that, it's going to give me 5 cosine 5x. Okay, I'm using chain rule. And differentiate the denominator, we're going to get 3. And now let's try the direct substitution. If I substitute 0 in place of x here, I'm going to get 5 times cosine of 0. And that is going to give me 5 times cosine of 0, which is 5 times 1. Okay, because cosine of 0 is 1. So it's going to give me 5 over 3. And that's your answer to this question. So this one is equal to 5 over 3. Okay, so that's how simple it is. That's how simple Bernoulli's rule is. Okay, what I would advise you to do is just maybe show your direct substitution first and show that you do get an indeterminate form. And then once you make this step, or once you're using Bernoulli's rule, just say at the end by Bernoulli's rule. Okay, I'm going to write Bern rule. Right, so just to show the examiner or the person who's checking your work that, hey, I'm using Bernoulli's rule because I got an indeterminate form. Okay, so that's one way to solve this, and that's the way I advise you to solve this. Let's try another way. Okay, so let's assume that in this example, you didn't know what Bernoulli's rule is. How would you try and do this? So we go to step 2, basically. We try and manipulate this expression into a form where we can make a direct substitution, or where we can use one of these special trig limits. And the special trig limit that I want to use, okay, notice how I have a sign in the numerator and a variable in the denominator. So what I'm thinking of is limit as, and I'm using a here. Okay, I'm going to use a, and you'll see why. Limit as a approaches 0 of sine a over a, that is going to be equal to 1. Okay, I'm just using a here instead of x, so you don't get confused about the x's in the question. Okay, so what we have is limit x approaches 0 of sine 5x over 3x. So how are we going to try and manipulate this to get it into this form where this, and this all are matching, and then that's going to be 1, right? How do we do that? So let's take a look. Look at the argument of sine, it's 5x. So what I need in the denominator is 5x as well. Now I want you to take a minute and think, how do I get 5x in the denominator? Okay, well, what if I pulled the 3 out as a factor? So I'll just pull this 3 out as 1 over 3 times this fraction. It's not changing the meaning at all. But I can do you one better. I can take this 3 out of the limit because it's a coefficient, basically. It's constant. Okay, so there's the 1 over 3 here in the front, not affecting us solving this limit right now. Okay, so that's great. And now, why don't I just put a 5 in front of the x and I'll get 5x? Okay, but we can't just do that. I put a 5 in the denominator, or basically multiply the denominator by 5. What I need to do now to maintain the value of this expression is I also need to multiply the numerator by a 5. And why can I do this? If I have done this, what I'm effectively doing is multiplying this original expression by, so let's use a dot for multiplication, by 5 over 5. And 5 over 5 we know is 1. When I multiply an expression by 1, I'm not changing the value of that expression. So what I'm doing is I'm just getting a 5 in the denominator and a 5 in the numerator, multiplying this expression by 1, not changing its value. That's great. So this matches with that. But we have a constant here, and we don't really have a constant or coefficient, if you want to call it that, in front of our standard special trig limit. So what I can do is, it's no big deal. Let's just take this constant out and put it with our fraction, because it is a constant after all. So now our fraction will be 5 over 3. Okay, and now for the last part, we need to change that, of course. We need to change that to 5x. How are we going to do that? And it requires a bit of thinking. So our limit is when x is approaching 0. What I want you to do is draw a Cartesian plane and draw the function 5x. So it looks like that. It's cutting through the origin, and it has quite a steep slope because it has a steep slope of positive 5. As x approaches 0 of this function y is equal to 5x, what is the function value approaching? Okay, you can see that it's approaching a 0 value as well. So what we can say is, as x approaches 0, 5x is approaching 0. So if I took the limit as x approaches 0, it would be the exact same thing as the limit of 5x approaching 0 as well. So what I'm going to do is, I'm just going to write this line out, and then I'm going to write out the limit again. So it'll be 5 over 3, copy that as is, limit as 5x approaches 0 of sine 5x over 5x. Why Why can I go from x approaches 0 to 5x approaches 0? Because if x is approaching 0, we know that the function 5x is also going to approach 0. Okay, that's an approach sign and arrow. Okay, so that's why we can do that. We could also make a new variable and say u is equal to 5x, and as x approaches 0, then we'll have u approaching 0 as well, and then in that case, this would be u, this would be u, and this would be u. But I don't really like using new variables if we don't need to. I think the concept is clear. As x approaches 0, 5x also approaches 0. So there's no need to do additional work and make it even more complicated. Okay, so that's what we have. Now, look at this. We have the same here, we have the same here, and we have the same here. So this entire thing here within brackets that I've just highlighted, that's going to be 1. So it's going to be 5 over 3 multiplied, again, dot for multiplication, multiplied by 1. That's going to be 5 over 3. The same exact answer that we got when we used Bernoulli's rule. Okay, obviously Bernoulli's rule is easier, but if you didn't know it and you wanted to use this method, that's how you do it. All right, let's move on to the next example. Okay, so take a look at example 2, pause the video if you want to try it, and then I'll go through the solution. All right, let's go for this one. So it's a trigonometric limit. The first thing that I want to do, the first thing that comes to my mind is let's check if we can use Bernoulli's rule. So let's make a direct substitution. We see that x is approaching 0. Let's substitute 0 into our numerator. We're going to get sine squared of 3 times 0. So 3 times 0, that's going to be sine squared of 0. And we know that sine squared of 0 is going to be 0. Okay, and then the denominator, let's get our calculator for this. So take take 0 and substitute it in place of x, and we will get 0. So the denominator is also going to be 0. So great, we have an indeterminate form. We can use Bernoulli's rule. So this is how we do it. We're going to have the limit as x approaches 0 of sine squared of 3x over x. And because this is going to yield an indeterminate form, when we do the direct substitution, we can use Bernoulli's rule. So Bernoulli's rule is keep the limit the same, don't change that at all, just differentiate the numerator. Now, if I had to differentiate the numerator, let's go through it. So we're going to have to use chain rule. The numerator is sine of 3x all squared. Now, this is how we differentiate it. Okay, let's make some space so we can differentiate it properly. Here we go. So it's going to be 2 into sine of 3x multiplied by cosine of 3x, and then it's going to be multiplied by 3. So I'll put the 3 in the front. Okay, well, let's put it at the end since that's how we would differentiate using chain rule. Okay, so it's going to be 2 times sine of 3x times by cosine of 3x times by 3. That's how we are going to use, that's how we differentiate using chain rule. So if I had to simplify this, it is going to be 6 times sine of 3x cosine of 3x. Right, and then if you had to differentiate the bottom, differentiate x, you're going to get 1. Okay, now we can just make the direct substitution. So let's try. Okay, so we see that x is approaching 0, so substitute 0 wherever you have x. Okay, so sine of 3 times 0, this entire term is going to be 0. I don't need to solve anything else because I have 6 times by 0. And then if you want to, you can solve cosine. Okay, it's going to be cosine of 0. That's going to be 1 all over 1. These are multiplication signs. And this entire thing is going to be 0. So a bit anti-climatic. Our answer is 0, but that's just how it is. Okay, so there's your answer. Your final answer is 0. Okay, so that's how you use Bernoulli's rule to solve this example. Now, again, what if you didn't know Bernoulli's rule? Okay, so you'd go to step 2 automatically if you didn't know Bernoulli's rule. Okay, from the guidelines. How you could solve this example without Bernoulli's rule, even though it's a bit tricky, is what you would have to make use of is the fact that cosine of 2a, okay, we're going to use a double angle identity, and that's what I mean by manipulation of this expression. cosine of 2a is equal to 1 minus 2 sine squared of a, right? And then we would solve for sine squared of a because we have a sine squared here. So we would find that sine squared of a is equal to half into 1 minus cosine 2 of a. So it means that I can replace this term on the top here with a term involving 1 minus cosine 2 of a. And that looks familiar. That looks like one of the trigonometric special limits that we saw on the first slide. And then I can use that fact, and I'll go through it right now. Just in case you're wondering why I'm not using sine x over x, and that limit is equal to 1. It's because we have sine squared of 3x. Okay, so we have, okay, so this should be 3x. Okay, we have two terms of this. Okay, sine 3x. That's how we have sine squared 3x. There's two terms. It's going to be very hard to manipulate them and work something with just sine x on its own or sine of 3x on its own. So the only way to do it is to get it in terms of cosine and use that second special trigonometric limit. Okay, so let's go for it. So the limit as x approaches 0 of sine squared 3x over x is equal to the limit as x approaches 0. And for the sine squared 3x, I'm going to use this, okay, this trigonometric identity on the top. So it says that sine squared of a, in this case, our a is 3x. So just write that out in pencil on the side. Our a is 3x is equal to half. Okay, so it's going to be half in the numerator. But what I'm going to do is I don't want to write that half in the numerator. So let's take that half out and write it in the front of the limit because it's a constant. So it's going to be half of the limit as x approaches 0. Okay, that half came from here. Of the numerator is going to be 1 minus cosine of 2a, 1 minus cosine of 2 times, what was our a? Our a was 3x. So 2 times 3x is going to be 6x. Okay, so we have a 6x here. And then the denominator stays as is. That's going to be x on its own. Right, so this here can be simplified to this here. And now it's really simple. You see we have 6x here in the argument of cosine. We want a 6x here on the denominator. So I'm going to multiply the denominator by 6. But I also need to multiply this entire numerator by 6. Okay, but what I'm actually going to do is I'm going to multiply that numerator by 6 by writing the 6 in front of the entire limit. Okay, because let's look at it. If I have that 6 in front here, I can just pull it out of a constant and it goes to the fraction. Okay, so that fraction in the front is now 6 over 2. That's going to become 3. Right, and then for the same reason, okay, let's take a look at the argument in the limit. If x approaches 0, it implies that 6x is also going to approach 0. If you want to prove it to yourself, draw the function 6x, look at what happens when x approaches 0. The function also approaches 0. So I can change that to the limit as 6x approaches 0. Now, take a look at this limit. We have the same here, the same here, and the same here. So we basically can just simplify this entire thing here to become 3 multiplied by, let's use a dot for multiplication. This entire limit in the blue brackets becomes 0, and you get the same answer that you did when you used Bernoulli's rule. Again, Bernoulli's rule is easier. I prefer if you use that, but if you don't know it, then you can use this example. All right, let's move on. So pause the video, try this example, and then I'll go through it. All right, let's do this solution. So we're going to use Bernoulli's rule for this. We're going to check if this is first and in determinate form. So if you substitute 0 in the numerator, you'll get sine of 0, that will be 0. And if you substitute 0 into the denominator, you're going to get 0 plus tangent of 0. That's going to be 0 plus 0 because tangent of 0 is 0. Bingo, we have an indeterminate form. Great, let's use Bernoulli's rule. So this is how it works. The limit as theta approaches 0 of sine theta over theta plus tangent theta is equal to the limit as theta approaches 0 off. Okay, so how Bernoulli's rule works is we now need to differentiate the numerator to get our new numerator, and the derivative of sine theta is going to be cosine theta, and then differentiate the denominator. So it's going to be 1 plus the derivative of tangent theta is secant squared theta. And now we are going to try and see if direct substitution works. Okay, so if I substitute 0 in the numerator, I'll get cosine of 0. That's going to be 1. Okay, and then I'm going to have 1 plus secant squared of 0. Okay, take a minute, try and figure out what that is. It is also going to be 1. Okay, so this entire answer is going to be 1 over 2. Right? And that's how you handle this example. Okay, in case you're having a problem with the secant squared theta, this is how I would do it. So think about what secant is. Okay, secant, right? Secant theta is 1 over cosine theta, right? So you have secant of 0. Okay, not okay, so you have secant of 0. That's 1 over cosine of, why am I writing theta in place of 0? Okay, that's 1 over cosine 0. Now cosine 0 is equal to 1. So we basically have 1 over 1, that's 1, right? Now what is secant 0 squared? It's basically 1 squared, and that's still 1. So that's why this answer is 1 here. Okay, so that's how you handle this example. The final answer, 1 over 2. All right, let's move on to example 4. Okay, pause the video, try it, and then I'll do the solution. All right, so again, let's use our general guideline. We are going to check if we can use Bernoulli's rule. So substitute 0 into the numerator. Cosine of 0 is 1 minus 1. That's going to be 0. So the numerator is 0. Things are looking good so far. Then we substitute 0 into the denominator. We get 2 times by 0 squared. We don't need a calculator for that. That's going to be 0. So great. We have an indeterminate form, 0 over 0. Let's use Bernoulli's rule. So this is an indeterminate form. The limit as x approaches 0 of cosine x minus 1 over 2x squared is equal to, and now we need to write out limit as x approaches 0, and now we need to differentiate. Okay, so differentiate the numerator. The derivative of cosine of x is minus sine x, and the derivative of negative 1 is 0, so we don't need to write that out. And then we need to differentiate the denominator. 2x squared, its derivative is going to be 4x. Now let's check if we can make a direct substitution. Okay, so for this example, we can't make a direct substitution. Okay, because if you had to take 0 and put it in place of 4x, okay, you're going to get 0 on the bottom, and on the top, you're going to get minus sine of 0, that's going to be 0. So you get another indeterminate form. Since you have another indeterminate form, you're again going to use Bernoulli's rule. Okay, so this is going to be equal to the limit as x. So this one also. So this one gave us an indeterminate form. And when we use Bernoulli's rule, it still gave us an indeterminate form. Let's try and use Bernoulli's rule again. It's going to be the limit as x approaches 0 of, differentiate the numerator. It's going to give us minus cosine of x. The derivative of sine is cosine, and then you just have a minus sign in front of it, so it's minus cosine. And then the derivative of 4x is going to be 4. Let's check if we can use a direct substitution now. So substitute 0 in place of x here. We're going to get minus cosine of 0. That's going to be minus 1. And the bottom is going to be 4. And we get a valid answer. Okay, we no longer get an indeterminate form. So the answer to this question is minus 1 over 4. Okay, and that's how you handle this example. So in this example, we had to use Bernoulli's rule twice. Once, because when I made a direct substitution for that one, it gave me an indeterminate form, 0 over 0. And then again, because when I used Bernoulli's rule, the new function or the new limit also gave us an indeterminate form when I used 0 over 0. Then I used Bernoulli's rule for a second time, and we got this. When I made a direct substitution, we got a valid answer of -1/4. Okay, so that's how you handle example 4. Let's go on to the last example. Okay, so you know what to do. Take a minute, try this one, and then I'll go through the solution. Okay, so again, let's check for Bernoulli's rule. If I have to substitute pi/4 in place of x, I'm going to get 1 minus tangent of pi/4, that is going to be 1. And then sine of pi/4, that's going to be √2/2. And then cosine of pi/4, that's going to be √2/2. So in the numerator, I'm going to have 1 minus 1, that's 0. In the denominator, I'm going to have √2 minus √2, that's also going to be 0. So excellent. I have an indeterminate form, 0/0. Let's use Bernoulli's rule. Right, so it's going to be the limit as x approaches pi/4. Let's just differentiate the numerator. So if I have to differentiate the numerator of 1 minus tangent x, the derivative of tangent is secant squared, and I have minus tangent, so it's going to be minus secant squared x. And then the derivative of sine x is going to be cosine x. And then just be careful when you're differentiating minus cosine x. So the derivative of cosine of x is minus sine of x. But you have a minus the cosine x. So you have a minus of the cosine x, and its derivative is minus sine of x. So on the bottom, you have a minus times a minus, it's plus sine of x. And that's how you differentiate the denominator. Now, let's try a direct substitution. So let's work with the secant squared of x. If you have to substitute pi/4 into secant squared, you are going to get -2. And if you have to substitute pi/4 into cosine of x, you're going to get √2/2. And then substitute pi/4 into sine of x, you're going to get √2/2. So the denominator is √2/2 plus √2/2. That is going to be √2 in the denominator. And now let's just rationalize this. So multiply this entire thing by √2/√2. You're going to get -2 times by √2/2. That's equal to -√2. And that's how you handle this example. So the answer to this one is -√2. Okay, so that's how you handle this example. Just let's go through the negative secant squared x, just in case you don't understand how I got that to be 2 on top. So think about what we have first. We have negative secant squared. Great. Let's work out what secant of pi/4 is. Well, I know that secant of pi/4 is the same as cosine of pi/4. And I know that cosine of pi/4 is √2/2. So secant of pi/4 is 1 over √2/2. I can rewrite that as 1 divided by √2/2. That would become 1 times by 2 over √2. Okay, so we can see that secant pi/4 is going to be 2 over √2. Then we want secant pi/4 squared, so I basically have to square this term. It's going to be, so the 2 squared would be 4, and the √2 would be 2. So it's going to be 4/2. That's going to be +2. And then I want negative secant pi/4 squared. And obviously we get -2. So that's how I got -2 in the numerator, just in case you were confused about that. Okay, so that's how you handle this example. That's how you handle trigonometric limits. Hope you enjoyed this video.